of the argument, right? F is the argument of the functional, x is the argument of its argument, and the functional derivative is a regular function of the argument of the functional. So the value that the functional derivative acquires at the points of the discrete points at which you have discretized its argument is basically the ordinary partial derivative of the approximation of the discrete approximation of the function. This is useful in practice. If you want to calculate in practice functional derivatives of functionals like this, it is a good idea to discretize first and then to calculate functional derivatives in this way as ordinary partial derivatives of the approximated functionals.
What is this h?
What?
What is this little h? 1 over h?
H is the discretization step here. Is the distance between two consecutive points of the discretization. Okay. Is x2 minus x1 or x3 minus x2.
So you mean that if I take points not evenly, then can I still do it?
Say it again.
I mean that.
This is if they're not spaced equally. What do you do?
I mean that now x1 to xn you will take these points evenly spaced, right?
Yeah.
So is it necessary? I mean, if I do not take these points.
If they're not equally spaced, there would be a different h for different points. Okay. Good question. Another rule of thumb for calculating partial derivatives is by this formal definition that would require a lot of mathematical definitions that I'm not even able to talk about. There is an error here. Here you have a plus here. This is not a minus. This is a plus. So the rule is the following. You want to calculate the functional derivative of a functional. This functional derivative is a function of the argument x, right? Then the rule of thumb is you take the value that the functional acquires at the function displaced a little bit by a Dirac delta function. You subtract the undisplaced functional and you divide by epsilon. You take the limit epsilon going to 0 and you get the functional derivative. This is basically an extension of the obvious concept of partial derivative. If you have a function of many variables, then the partial derivative is the differential increment, where here you have the f of I plus, not minus, epsilon delta ij divided by epsilon. If you pass to the continuum, then you have infinitely many arguments here, and the Kronecker delta ij will become a Dirac delta. I will recommend that those of you who are not familiar with this try to apply either of these two definitions to the functionals given before. Try to calculate by yourself the functional derivative of these two functionals, or even for this. This is tricky. The first one, which seems the simplest, is actually tricky. But try this as well. Calculate the functional derivative of these three functionals using either one of these two definitions. Okay? And you may want to try other functionals. You invent some crazy rule for calculating numbers out of functions, and you exercise yourself to the calculation of functional derivatives. Hellman-Feynman. So, quantum mechanics, density functional theory, many theories in the physical sciences and in engineering as well, result from variational principles. Variational principles say that the quantity or that you are interested in, or a function that you are interested in, are such that they make stationary some function or some functional. For instance, the Schrödinger equation that is the eigenvalue equation for some Hamiltonian results from the Ritz variational principle that says that the expectation value of the Hamiltonian over some state with the constraint that the state is normalized is stationary. Suppose that the Hamiltonian that you want to minimize, of which you want to calculate the extremum, depends on some parameter. For instance, molecular Hamiltonians, such as we have described before in the context of the Born-Oppenheimer approximation, depend on nuclear coordinates as parameters, right? So it is the energy as a function of the nuclear coordinates may be seen as the solution of a variational principle where the functional that you want to extremize depends on a parameter. So it is meaningful to ask yourself what is the derivative of this extremum with respect to the parameter of upon which the functional depends. In this case, the function is a simple quadratic functional, and the dependence is through the Hamiltonian. So let me make a formal statement, because the Hellman-Feynman theorem is way more general than it is usually described in textbooks. And it is a very powerful concept, very simple and very powerful. So pay attention to the next 2-3 minutes, pay particular attention to the next 2-3 minutes, and wave your hands if I'm not able to get properly understood. This is very important. So suppose that you have a functional or a function that depends parametrically on a parameter lambda, and you want to find the minimum of that function or functional with respect to another argument x. The value of the minimum of that function as a function of lambda determines a function of lambda, right? This is an abstract statement of what I have just written here. So the energy as a function of the nuclear coordinates is nothing but the value of the minimum of the expectation value of the Hamiltonian over the wave function as a function of the parameters, that is, as a function of the nuclear coordinates. Now, remember, in the Born-Oppenheimer equations, the first equation, the equation of motion, requires the calculation of the derivatives of the energy with respect to the nuclear coordinates, that are the forces acting on nuclei. Those derivatives, formally, what are they? They are nothing but the derivative of the value of the extremum of this functional or function with respect to the parameter. Okay? So it is important and very general, a very general problem, to know how to calculate derivatives of extrema of functions with respect to the parameters upon which that function may depend. This is the general target of the Hellman-Feynman theorem, or the generalized Hellman-Feynman theorem. How would you how would you calculate this, the value of this function? Of course, you have first to calculate the extremum, and the extremum is given by the vanishing of the partial derivative of this function with respect to the argument with respect to which you want to extremize the function. This gives an implicit dependence between x and lambda, of course, right? This is an equation equating dg over dx to 0 is an equation that relates x, the first argument, to the second, and gives an implicit dependence of x upon lambda. So, g of lambda, that is the value of the minimum, is nothing but the value, by definition actually, the value that the function acquires at the position of the minimum. The position of the minimum is an implicit function of the parameter, right? Is this clear? It seems trivial to me, but I want to make sure that this is trivial to everybody. Can I hear a yes or no? Yes. Yes. Clear? Clear. Okay. Then let us calculate explicitly the derivative of this. The derivative of this, you have to use the chain rule, right? You have this is a function of two variables, and then you have to differentiate with respect to the first variable times the derivative of the first variable with respect to lambda, plus the derivative with respect to the second. Right? Simple chain rule for derivatives. But now you use the fact that dg over dx is 0, because this is the definition of x of lambda. Right? So dg over dx is 0. This is the Hellman-Feynman theorem. The Hellman-Feynman theorem basically states that if you want to calculate the derivative of the extremum of the function with respect to a parameter, you have only to calculate the explicit derivative, not the implicit one. You have an explicit derivative, that is the partial derivative with respect to the parameter itself, plus an implicit derivative, that is the derivative with respect to the other argument times the derivative of the argument with respect to the parameter. But the implicit derivative is 0 because of the stationarity of the function or of the function. If you use this argument for the Ritz functional, the one appearing in quantum mechanics, you get basically the Hellman-Feynman theorem that says that the derivative of the eigenvalue is equal to the expectation value of the derivative of the Hamiltonian. In principle, you would also have derivatives of psi, because this functional here, where it is, depends on lambda through h and also to psi. But you have the derivative with respect to h, the derivatives of h, and that's okay. But the derivatives of psi with respect to lambda would cancel because of the stationarity of the problem.
I have a small question. See, in normal variational theory, like in helium atom and so on, we just take the derivative with respect to the parameter. But is this Feynman-Hellman theorem has any limit to the variational principle, ordinary variational theory? Can one correlate this? This is for a functional. But in ordinary variational theory, like when we apply for helium atom, we just take the derivative with respect to the parameter and then find the screening of the electron. Now, what way this Hellman-Feynman theorem is related to the ordinary variational theory? Is there any relation?
I'm afraid I don't understand the question.
See, in helium atom, when we use the variational principle, we usually look at the extremum. Basically, we minimize the energy and find out the ground state energy. Now, in using Hellman-Feynman theorem, we basically take this as a functional. Now, is there any condition that the Hellman theorem is more general than variational principle? Is there any correlation between these
Well,
two?
the Hellman-Feynman theory strictly applies if the space of functions in which you search the minimum does not depend on the parameter. If this space of functions depends on the parameter, then you have to take into account an explicit derivative as well. This is the origin of the so-called Poolai forces. The Poolai forces come from the fact that if you make a finite basis expansion of the wave function, for instance, for the helium atom or any other system, the basis functions may depend on the parameter. They may or may not. If you had a complete set of states, of course the dependence would be irrelevant, because all the states would, so the basis set would span the entire Hilbert space independently of the value of the parameter, of the nuclear coordinates or whatever parameter you want. But if you have a finite dimensional basis set, it may happen that the space, this manifold spanned by the basis set depends on the external parameter. In that case, the Hellman-Feynman theorem does not strictly apply, and you have to consider corrections to it that in the quantum chemistry literature are known as Poolai forces. Often wrongly pronounced Poulet. He's an Hungarian scientist, and he's called Poolai. A little thermodynamics, elementary thermodynamics. You will see in a while what thermodynamics has to do with density function theory. Suppose you have a system, a liquid or a solid, whatever, and you calculate the energy of that system as a function of the volume, and possibly as a function of some external field that I indicate as X. This may be an electric field or some internal constraints that you may want to apply to your system. Of course, in thermodynamics, you are free to choose whatever extensive or conjugate intensive variable you want to describe your system, right? You may want to describe your system as a function of the volume, but you may want to describe the system, for instance, as a function of pressure. What is the pressure? The pressure is basically the derivative of the energy with respect to volume. And when you change the description from volume to pressure, what would standard textbooks say? They say that you have to perform a Legendre transform. The mathematical operation that transform a function of the volume as another function of the pressure, that is, as a function of the conjugate variable, is called a Legendre transform. Let us see what are the properties of the Legendre transform. Legendre transform, this is the enthalpy. The Legendre transform of the energy is the energy plus PV, and this is called the enthalpy. This is all thermodynamics is basically a trivial application of these rather sophisticated mathematical concepts that is called the theory of Legendre transform. The first important property that is key to the theory of Legendre transform is that if the energy as a function of volume is convex, then it's the derivative of the energy with respect to the volume is monotonic. It is either increasing, either decreasing if it is convex, or decreasing if it is concave. So convexity basically implies that the relation between P and V can be inverted, right? You have a one-to-one correspondence between the independent variable and its and the derivative of the energy with respect to the independent variable. Very important concept. Keep this in mind for the following. This is very relevant to density functional theory. So when a function is convex, then the relation between its argument and the partial derivative is invertible, right? If it was not convex, if it was wiggly here its derivative would oscillate and you could not invert it. But convexity implies invertibility. Very important property. The second important property is that this transform can be formally seen as the result of a variational search. So this enthalpy can be seen as the maximum of E as a function of V and X plus PV. You see that if you if you search the maximum here, you make the partial derivative of this function E plus PV, and you would obtain dE over dV plus the derivative of PV, but the derivative of PV with respect to V is P. So the equation for the extremum of this is nothing but that. Okay? So that definition of P equal to the derivative of energy with respect to volume basically allows you to see the Legendre transform as a variational principle by itself. Because it is the Legendre transform is the result of the variational principle, the Hellman-Feynman theorem applies. So if the original function energy depends on a parameter, its partial derivative, the partial derivative of the Legendre transform is equal to the partial derivative of the energy itself. Also, you can demonstrate, I will not do this, that starting from a convex function, a convex energy, you will end into a concave enthalpy. And finally, the energy can be seen reversely as a variational principle starting from the enthalpy. Basically, you have that the Legendre transform of a Legendre transform is the function you started from. So you start from E, you do a Legendre transform, you get H, you do another Legendre transform on H, you go back to E. Not that I have demonstrated anything. I have just listed the 2-3 facts that you may find explained into textbooks or in places that I would be glad to suggest to you for further lectures. But keep in mind these properties. These are important for DFT. This has nothing to do with DFT. This is mathematics, Legendre transform, and elementary thermodynamics. But it is relevant to DFT. Let us go to DFT. So let us start from the Hamiltonian, the electron Hamiltonian, kinetic energy, electron-electron interaction, external potential. Then let us define a functional that I call the Schrödinger functional. A functional that is the minimum of the expectation value of the Hamiltonian over all the possible normalized wave functions. Of course, this functional depends parametrically on what? On the potential. You give me a potential, I solve the Schrödinger equation for you, and I return the ground state energy for that Schrödinger equation. So I return a number in exchange of a function. What have I done? I have done I have defined a functional, right? So, the ground state energy of a system is a functional of the external potential. Doesn't take density functional theory. This is just an elementary concept deriving from the fact that you solve the Schrödinger equation. Nothing but this. Now, the very important two properties that would lead straight away to DFT are that this functional is convex. I will not demonstrate this, but believe me, it is so. And for those of you who are interested, I will give privately or in small groups a demonstration. It takes 10 minutes to demonstrate it. It's not difficult at all. This functional is convex. Also, this functional depends, we have seen parametrically, on the potential, and it is reasonable to ask yourself what is the functional derivative of this functional with respect to its argument, to the potential. Then you have to apply the Hellman-Feynman theorem. Very simple, because this is, you minimize with respect to psi, but this functional here, in this functional, v is a parameter. So the derivative of E with respect to v is equal, you have only to take the derivative of the functional, the explicit derivative. You don't have to take the implicit derivative. So you don't have to calculate this partial derivative, you don't have to differentiate psi with respect to v. Of course, psi depends on v. But in the calculation of the functional derivative of E with respect to v, because of Hellman-Feynman, you have to take only the explicit dependence. And the explicit dependence, you do the functional derivative of this, the functional derivative of course, this term here does not depend explicitly on v. Depends implicitly, of course, through psi, but not explicitly. The only explicit dependence in this is in this coupling of the potential to the density. What is the functional derivative of the integral of rho times v with respect to v? It is rho, right? So the functional derivative of E of v with respect to v is the density. This is a complicated way of stating first order perturbation theory. Think about the definition, the first definition that I gave of the functional derivative, and you will convince yourself that this is nothing but first order perturbation theory, quantum mechanical first order perturbation theory. So home assignment, what has this, answer the question, what has this to do with first order perturbation theory? Find it out. If you cannot, come to me and we will discuss this together. Consequences. This functional is convex. This means that the correspondence between the argument and the first derivative is invertible. There is a one-to-one correspondence between pressure and volume, between conjugate variables, but the density is the conjugate variable of the potential. Then there is a one-to-one correspondence between potential and density. This is the first Hohenberg and Kohn theorem. Just a simple consequence of the convexity of the Schrödinger function. Second consequence, you can define the Legendre transform, because the function is convex, you can define the Legendre transform. And this Legendre transform, if you subtract from E the product of V times its conjugate variable, you basically drop this. And what remains is the expectation value over the ground state of the kinetic energy plus the electron-electron interaction. What is this? This is the Hohenberg and Kohn universal functional of the density. Third important consequence, if starting from this Legendre transform, f of rho, you go back to to the original Schrödinger functional, that is the ground state energy corresponding to the functional, then you get it from a variational principle, because Legendre transforms can be defined in terms of a variational principle, and you get that the ground state energy of a system is can be seen as the minimum of this functional plus the coupling of the potential times the density. And this is the second Hohenberg and Kohn theorem. Simple and beautiful. I find not that it is very useful, but it is a different way of looking at Hohenberg and Kohn theory that I like very much. So I wanted to share this with you. Of course, in order to calculate this f of rho, you should calculate E of v first. You have to solve the Schrödinger equation first, and you wouldn't go anywhere, because this wouldn't help to solve your problem if you have not practical ways of approximating this Legendre transform, this f of rho. And this is, I think, the real stroke of genius of Walter Kohn and Lushan. A practical way of, at least conceptually, devising a way of mapping this unknown functional onto something that can be calculated at least in principle. So let us do the following. Let us define this functional, this universal functional, in the following way. We split off the value that the functional would have for non-interacting electrons. So this Hohenberg-Kohn theorem and Legendre transform and stuff can be done both for interacting and non-interacting electrons. And for non-interacting electrons, the functional f of rho is something that you call T naught. Right? This is the name we give to the Hohenberg-Kohn function for non-interacting electrons. Then we, if the electrons do interact, they will have a kind of classical electrostatic interaction that has this obvious form. Of course, the total functional is not equal to the sum of the non-interacting functional plus the classical electrostatic energy. There would be some missing term, which we cannot calculate. The name we give to what we cannot calculate is the exchange correlation function. This is nothing magic. It's just the name we give to our ignorance. We know how to calculate T naught, we will see in a while. We know how to calculate the classical electrostatic energy. This is trivial. The difference between what we can calculate and what we cannot is given a magniloquent name as the exchange correlation function. Actually, the exchange correlation function should be more appropriately called the ignorance function. It's the name that we give to our ignorance. And actually, Richard Feynman, in his statistical mechanics textbook, when he describes the homogeneous electron gas, he calls the correlation energy the stupidity energy, because it's the name we give to our inability to calculate something. That's the stupidity energy, according to Richard Feynman. So let us solve for the variational principle of this. We take the functional derivative of this, we take the functional derivative of this, calculate this with the rule of thumbs that we have given a few slides ago. Do calculate explicitly the functional derivative of this and convince yourself that this is that. Okay? And then you have the functional derivative of this unknown functional, the external potential equal to the chemical potential, that is a constraint that we introduce to account for the normalization. So instead of searching over all the possible densities, we search over the densities normalized to a pre-assigned number of electrons, and this will introduce a Lagrange multiplier. of course, if you look at this, this is what? This is nothing but a function of R. And now we have just to look at this variational equation with different eyes. This is the equation that I would write for a system of non-interacting electrons, to which this T0 function I refer. If instead of being in the field of the external potential V, it was in the field of V plus this auxiliary potential. But we know how to solve this without a density functional theory. We have just to solve the one electron Schrödinger equation, for which we can calculate the density. So Kohn-Sham is nothing but a kind of detour. We start from density functional theory. Then by this very clever trick of splitting off what we can calculate from what we cannot, we map the density, the variational principle of DFT back onto a quantum mechanical problem, but a quantum mechanical problem that we can solve because it is a non-interacting quantum mechanical problem. There is no longer any interaction. And this can be solved if only we knew the exchange correlation, the stupidity function. Of course, the stupidity function is not known. We have to resort to approximations to it, but this is another story. And we will basically rely on very elementary approximations, such as the local density approximation or the generalized gradient approximation, that are approximations whose limitation are partially known and partially still the subject of very intense research. I'm doing very, very late. So what I will do, I will go on for another 10 minutes. Then I will ask you the favor to shorten a little bit the coffee break, of taking, instead of half an hour coffee break, a quarter of an hour coffee break, and I will make one other quarter, 15 minutes talk after the coffee break. Sorry, but I went out of, I ran out of time.
I think you started 15 minutes late too.
Okay, even better. Okay. I will not feel too guilty, so the result for them is the same. It's only just thank you for trying not to feel me, to make me feel too guilty. Okay, so all this. So we start. Let us make the point. We started from quantum mechanics and interacting electrons Hamiltonians. We went over DFT and the functional of the density. Then we have made a small step back to quantum mechanics, fake quantum mechanics, the quantum mechanics of a fake system, but a system that is of non-interacting electrons. So basically, what we solve is not in actual practical DFT, is not a variational problem for the density. It's a variational problem for the quantum variables of the auxiliary system. What are the quantum variables of a system of non-interacting electrons? It will be the orbitals, the one electron orbitals of the system of non-interacting electrons. So what we really solve is a variational principle not quite for the density, but for the set of occupied Kohn-Sham orbitals, whose number is equal to the number of electrons because of the Pauli principle, the Aufbau-Prinzip, that you have a number of occupied states equal to the number of electrons. You put one electron for each available state until you fill all the energy, all the levels up to the Fermi energy. So basically, the equations that we solve in practice are variational equations for the orbitals, for which we determine the minimum of this functional that depends parametrically on the density, on the nuclear positions, under the constraint that the one electron orbitals are orthonormal. So in the many-body formulation, you have just one condition to fulfill, that is the normalization of the one wave function that you have to find out. Here you have many wave functions to find, of a much simpler form though, but for them you have many more constraints to account, that is all the orthonormality constraints. So you do the functional derivative of E with respect to psi or psi star. You account for these constraints with Lagrange multipliers, and these are the equations that basically result from this variational principle. Conceptually, what you have to do is to realize that here you have these Lagrange multipliers that are a matrix, because essentially you have the number of Lagrange multiplier is equal to the number of constraints. The number of constraints is equal to the square of the number of orbitals or of electrons. So you have a matrix of Lagrange multiplier that depends on indices that label electronic states. It can be demonstrated that this matrix is Hermitian. It can be diagonalized, therefore, and it can be demonstrated that the value of this functional is invariant with respect to unitary transformation that mix the psi among themselves. So if you have a solution, say just two variables, psi 1 and psi 2, you take any unitary linear combination of psi 1 and psi 2, and the value of this functional would not change. Because of this, you are free to choose whatever representation you want in the manifold of occupied orbitals, and in particular you can choose a representation in which this matrix of Lagrange multiplier is diagonal. In that representation, this variational equation is nothing but the Kohn-Sham self-consistent equation, where this epsilon b are the eigenvalues of this matrix of Lagrange multipliers. How to solve this in practice? Of course, you have functional equations, and functional equations can be only solved if you give an explicit finite representation of the functions of the unknowns. So basically, what you do, you expand the Kohn-Sham orbitals into a basis of functions, and this array of linear coefficients uniquely determines the wave function once you have specified the basis. This is the variational equation we have started from, and the self-consistent eigenvalue Hamiltonian eigenvalue equation that results from writing down this equation in the basis that diagonalizes lambda is the Kohn-Sham Hamiltonian. Where is the Kohn-Sham equation? Where the Kohn-Sham Hamiltonian depends on the solution itself, because the Hamiltonian depends on the density, but the density depends on the wave function. The wave function are determined by this array of coefficients. So this is a Hamiltonian that depends on its own eigenvalues. This is why mathematicians call this a nonlinear eigenvalue problem. So it is an eigenvalue problem in which the operator or matrix that you want to diagonalize depends on its own eigenfunction. So what mathematicians would call a nonlinear eigenvalue problem, we physicists would call a self-consistent problem. Exactly the same thing, the same concept. So of course, once you realize that what you actually do when you solve this self-consistent problem is to solve a variational problem, then a whole new universe opens in front of you. because you can solve that same variational problem in any way you want. In particular, you can solve it dynamically. Suppose you walk in the mountains and you want to find the position of the minimum of the landscape, of the valley below you. What would you do? You just, if you are in the snow, you sit yourself in the snow and you slide in the snow, and the gravity would carry you along the direction of steepest descent. Friction would slow you down, and you would end up basically in the nearest bottom of the valley. The mathematical equations that describe the movement of a boy or a girl sliding onto a snowy slope is a first order differential equation because of friction that basically says that the velocity is always parallel to the force and opposite to it. This is the steepest descent equation. That is a dynamical way of finding, if you follow dynamically the boy or the girl sliding over on the slope, on the snowy slope, you will at infinite time, at very large time, when the boy or the girl stops, they will stop on the bottom of the valley. So this is a way of solving the Kohn-Sham equation without solving any eigenvalue equation. And this was one of the beautiful ideas of Karen Parinello back in '85. So the realization that you can exploit the variational nature of the Kohn-Sham equation to solve them dynamically rather than through a self-consistent equation. Whether or not it is more convenient to do this self-consistently or dynamically is a matter of discussion. I think that different people would give you different answers. My own answer would be that the self-consistent way is usually faster but less robust. That is, if it is well implemented, it is way faster than any dynamical approach that you may devise, but it is more unstable. So the dynamical approach always works. So it may be slow, but it is foolproof. So when you choose a basis set, you have to pay attention to different requirements. Completeness must be easily checked and systematically improved. Matrix elements should be easy to calculate, and or H-psi products easily calculated on the fly. This is because for large-scale eigenvalue problems, you never actually calculate the Hamiltonian because it may be too large. It may be thousands or millions of dimension, and you basically resort to iterative methods where basically instead of calculating and storing H, you calculate on the fly products of the Hamiltonian times the trial wave functions. Hartree and exchange correlation potentials should be easy to represent and calculate, and if you get an orthogonal basis set, that would be great. I'm really out of time. So last slide, and then we will stop for a coffee break. Among all the possible choices for basis sets, plane waves are our favorite choice. Plane waves are easily classified in terms of wave vectors that are chosen in such a way that the corresponding kinetic energy is smaller than some pre-assigned cutoff. By letting this cutoff grow larger, going to infinity, the basis set becomes more and more complete, so that the completeness is easily checked, and the basis is orthogonal, and normalization is also easily imposed. With plane waves, it is rather natural to deal with periodic boundary conditions. You have a system, you enclose it into a box, and by choosing this wave vector in such a way that these are multiple or 2 pi over the dimension of the box, you will get a periodic wave function. For finite systems, such as a molecule, periodicity is a fake. I mean, molecules are not periodic. But if you simulate molecules with plane waves, what you actually do, without even knowing this, if you don't, is to simulate a fake system where you periodically repeat the molecule in such a way as to fill all over the space. And these wave vectors are basically the vectors of the reciprocal lattice. For infinite crystals, instead, periodicity, the wave function is not periodic over the unit cell of the simulation, but it is periodic over the entire crystal. This is the essence of Bloch theorem, right? So basically, you have that the Bloch functions are given by products of functions that are periodic over the unit cell times a phase factor that is periodic over the entire crystal. And counting the number of allowed wave vectors gives you the concept of Brillouin zones, etc. Let us stop here for 10-15 minutes.
No, CIJ is, this does not.